Okay, welcome back. And we were talking about polarity in a bond based upon these electronegativity values. So let's label this chart electronegativity. And notice they all have some sort of value without a unit. Lithium has a value of 1.0. Fluorine has a value of 4.0. And what that means is that the fluorine nucleus pulls on the electron charge cloud 4 times as strong as lithium does. And so these values don't have a unit, they're relative values. You compare one to another. Again, if we take a look at nitrogen and compare it to fluorine, it's a 3 to 4 ratio. Nitrogen is highly electronegative, but it only pulls on the electron charge cloud 3/4 as strong as fluorine does. So again, this idea of polarity I went over with the B-Day class. This dipole moment. If we look at the bond between lithium and fluorine, actually, this is an old chart. I had memorized 0.96. The chart I just showed you has lithium at 1.0. We know that lithium has a lower electronegativity value than fluorine does. And so therefore, yeah, they're going to have an interaction of the electron charge cloud that creates the bond. However, that charge cloud is going to drift towards the fluorine. There's going to be a surplus of charge on the fluorine, a deficiency of charge on the lithium, and we call that a polar bond. In other words, it has, in terms of physics, a force, what's called a dipole moment. And we represent that dipole moment with a vector arrow. We put a positive symbol on the vector arrow over the element that has the electropositive value. And we draw the arrow towards the drift, which is going to be towards the electronegative material, in this case fluorine. And the symbol I tried to draw is lowercase sigma. It's supposed to represent the term pseudocharge. And so this would be what's called pseudopositive, and this would be called pseudonegative. Pseudo means that, look, yes, there's a deficiency on the pseudopositive, there's a surplus of charge on the pseudonegative, but it's not the same coulombic value as a pure -1 charge like an electron is by itself. But there is a disparity of the electron charge cloud. So we said look for polarity. We look for symmetry when we're talking about polarity. For instance, if they draw a cloud like this top one, where it's symmetrical, then we know that this is a covalent nonpolar bond. Right now you don't have to know covalent. Covalent's the only ones that could have nonpolar. But we would look at the symmetry and we would say nonpolar. The second example, this is asymmetrical. The smaller charge cloud is the pseudopositive. The larger charge cloud is the pseudonegative, and we draw the drift towards the negative charge cloud with the vector arrow, and this represents a polar bond. And if they completely separate the charges, we would call this an ionic bond. All ionic bonds by nature are polar. So this is probably a better depiction here. The bottom one being symmetrical, and asymmetrical would be polar, and ionic, they're always polar. However, they draw them as a separated charge cloud. Even though that's not correct. We'll see that these things form ionic solids and the particles are actually right next to each other, but it's not a bad way of thinking of it. Chemical reactivity. The basic periodic trend is that the elements with the highest and lowest electronegativities, when they interact with each other, they are the most reactive. So we're looking at elements that are on the far left interacting with elements on the far right. Those are going to have high reactivities, which means they're going to produce a lot of energy when they react. So highly exothermic. They use the term bond strength. Once the bond is formed, how much energy does it take to separate those charges again? In other words, break the bond. And your book takes a physics point of view of this. This is from our guy Linus Pauling. Remember the Pauli exclusion principle and the 4 quantum numbers. And so when they talk about strength of the bond, they're looking at it in terms of, hey, if we have to throw this into heat, if we have to throw this into fire or a blast furnace, how much energy does it take to break the bond? What's the lowest temperature we can use to break a mole of bonds? That's only one way of looking at bond strength. However, Harvard came out with a paper about 5 years ago. Yes, if you throw something into heat, then the ones that are highly electronegative, like sodium, and the ones that are highly electropositive, like sodium, and highly electronegative, like chlorine, are going to form strong bonds. In fact, it takes a temperature of 850 degrees Celsius to break those bonds. However, if you throw salt and water, the bond breaks right away. Salt dissolves in water into ions and ionizes. It takes very little energy because the water molecule pulls the ions apart. It says that whole sphere of hydration thing. So, you really have to take a look at the environment. We're going to go with this statement because it's in your book. So on a chemistry test, if they ask you bond strength, polar ionic bonds are going to be very strong, where covalent nonpolar bonds are going to be the weakest. However, in a water environment like the human body, your covalent bonds are the strongest. So don't be surprised. You take a bio test and they ask you about bond strength, that the covalent nonpolar, like carbon to hydrogen, is going to be the strongest because you're talking about a water environment. So it's okay in biology to say that carbon to hydrogen is strongest, but in chemistry, since we're talking about thermoheat, it's going to be hydrogen to fluorine. And the way you figure that out is you look up the electronegativity values. We look up hydrogen, and I think I recall it's 2.2. Fluorine is 4.0. So we have a very large dipole moment there. Whereas if we look up carbon, it has an electronegativity value of 2.4. Hydrogen is only 2.2. So we have essentially almost a non-polar bond there. It is slightly polar. And the truth of the matter is we should probably use the term slightly polar. I hate to say it this way because it's funnier in person, but I always consider polarity from a chemical point of view like pregnancy. You're either pregnant or you're not pregnant, so you're either polar or you're not polar in a bond. But in biology, apparently we care about how far along you are in the pregnancy. So in biology, they treat this carbon to hydrogen bond as though it's non-polar. Actually, it's slightly polar, and they say it's non-polar in biology because it doesn't react. Well, you take it out of the human body and throw it in a blast furnace, and I'm an organic chemist. I can get that thing to react. So, but on our test, hydrogen to fluorine would be the stronger bond. All right, bonding mechanisms and properties. So ionic, you have to have large differences in electronegativity. Covalent, you have small differences. But again, I'm going to go back to that thing that we talk about what's called bond character. There is no pure 100% ionic or 100% covalent bond. Again, if we talk about bond character and we say it's more than 50% ionic, that means that Q1 and Q2 are the most important thing in terms of Coulomb's law that makes that attraction. Whereas in covalent, what we're really focusing on is the d squared part of Coulomb's law, the overlap between the atoms. So again, there really is no such thing as a pure 100% ionic or covalent bond. This number is important. On a test, they'll ask you, hey, are these bonds ionic or covalent? And in the past, we've always said, well, metal to nonmetal, right, is ionic. Everything, nonmetal to nonmetal, is covalent. Well, that's usually true. But you have to take a look at the electronegativity values. There are some exceptions. Oopsie poopsie. Hey. For instance, if we go and take a look at a bond between iodine, which has an electronegativity value of 2.5, and magnesium, which has an negativity of 1.2, normally we'd say magnesium metal, iodine nonmetal, this must be an ionic bond. But if you take a look at the electronegativity difference, and we're just going to use the absolute value here, it doesn't matter what order you put them in, but we do 2.5 minus 1.2, and that gives us a value of 1.3. This is actually covalent. Has more covalent character than it does ionic character. All right, so in terms of these properties, ionic, large differences in electronegativity. Again, remember that 1.66 value, and it's usually metal to non-metal, but not always. High coulombic attraction. So these things take a lot of heat in order to melt. They form crystal lattices, which means they form salt crystals. And we're going to take a look at what a crystal lattice looks like in a moment. This is bizarre. If you melt them, you can use them to conduct electricity, although I don't want to live in a world where it's 850 degrees Celsius in order to conduct electricity. Copper wiring does it much better. So this would be a crystal lattice, where you have this repetition of the positive and negative charges, and it creates a three-dimensional shape. What they're showing here is what's called a simple cube stack. There's actually 20 of these different types of stacks. Some of them are rhombus in shape. Some of these crystals are octahedral in shape. There's a lot of different shapes, but the simple cube is the most common. And this would be a depiction. The purple would be the sodium, and the green would be the chlorine. So to make a salt crystal, you're going to stack each sodium next to 6 different chlorines. And if you're having trouble seeing it, here's my sodium, and then we have 4 chlorines around it. We have one to the north, we have one to the south, we have one to the east, we have one to the west. But there's also 2 chlorines that you can't draw here. There would be one right in front of the sodium, and there would be another chlorine atom behind it. So you have the sodium attracted to 6 other chlorines. That's a lot of charge interaction, creates a very strong bond. All right, the mechanism, as with all bonding mechanisms, you got to get the atoms close together. And then they say you transfer electrons from the metal to the non-metal. But again, why? Because metals tend to be highly electropositive, and non-metals tend to be highly electronegative, and positive and negative is a great interaction. This complete transference thing, it's not really 100% completely transferred, but it's very close to it. The metal is the positive, which we call a cation. The non-metal is the anion. Positive and negative creates the bond, coulombic attraction. All right, properties of covalent. Again, normally non-metals, but it can also occur between a metal and a non-metal that have very similar electronegativity values. Low melting points, although they don't dissolve very well in water, so they have stronger bonds in a water environment than they do in a heat environment. The difference between covalent and ionic is that when ionic form crystals, like I said, there's only about 20 different types of crystal shapes, but there are thousands and thousands of different shapes to the molecules. And that is because they can create a variety of what they call bond length and bond angles. Bond length, here's the definition for you to mesmerize. Distance between 2 nuclei along a bond axis, and the bond angle is the angle that's created by that axis. And I just realized, look at that word. There's something wrong here. My goodness, been using this slideshow for 20 years, and apparently this is an axis, and this is something that you use to chop down a tree. So I think this should be an eye. Anyway, all right, so here's a little picture of it. Again, the bond length is the distance between 2 nuclei that create a bond. And this would be the bond axis, would be a straight line between the 2 nuclei. And here we would take 2 bond axes, let's say between hydrogen and nitrogen, and this other one between hydrogen and nitrogen, and then this angle that's created in between there, let's call it theta. I don't know, because I just happen to like theta. That is the bond angle. And covalent, you get a wide variety of bond angles and bond lengths depending upon how well the atoms overlap each other. So therefore you get a variety of shapes. And in biology, we know shape determines function. So covalent compounds tend to be the things that give rise to life, because the more variety of function you have, the more likely the organism is to survive. All right, the mechanism, the step-by-step process. Again, we got to get them close together, and we're going to create a molecular orbital. So that's the term that they're going to use, molecular orbital. And that's going to be the overlap between the 2 atoms. the electrons have to be stuck in that area, and that makes these things brittle. You hit them, and the force of the, you hit a sugar cube, it breaks apart, again, because those electrons aren't free to move around. And then you hit them with stress, and they tend to fissure. And we're going to consider, once they overlap each other, that the electrons are shared. But like I said, there is a little bit of ionic mechanism there too, because positive nuclei attracts negative electrons. All right, so here's my little diagram. One atom overlaps the other atom, right? So we'll do blue for the other atom, and then the two electrons here get trapped in the overlap, and so therefore the blue electron is now not only attracted to its own nucleus, but it's also attracted to the red atom's nucleus. Third type of bond, metallic bond. Metallic crystals are a little bit like ionic, but they're actually a lot like covalent. The difference is that they are formed with metals, the same metal, usually. Your book says the same metals and that there's no compounds found. However, there are some compounds, especially between metals that have similar atomic radii, like zinc and copper. But for the sake of argument and for the sake of first level chemistry, we're going to say, well, at our level, all of these involve the same metal. So we can create a crystal out of all copper atoms or a silver crystal out of all silver atoms, but we're not going to mix silver with copper. The properties of the metallic bond are the same properties that we talk about with metals. They're shiny. You can conduct electricity and heat well with them. You can bend them into shapes without breaking, and we're going to find out that the electrons are not stuck in one area of overlap. They're actually multiple areas of overlap, and the electrons can move freely throughout the crystal, which makes them bendable. And they are good conductors of heat and electricity, and we'll discuss why in a moment. So we have an ionic crystal, again, a repeating array of positive and negative charges. Oopsie poopsie, time to stop. Okay, I'm going to pick this up on the third video.